In this final lesson we tackle the problem of likelihood-based inference. We start from the Gaussian distribution to achieve more advanced techniques, such as the model-based clustering. First, let's introduce the concept of random variable. The most common model in statistics is the Gaussian or normal one, which is suitable for continuous variables, positive or negative. The figure on the right shows the famous bell-shaped function that defines the Gaussian distribution. This is defined by means of two parameters, the mean mu and the standard deviation sigma. The former defines the center of the distribution, while the latter its variability around the mean. The larger is the standard deviation, the larger is the uncertainty, while smaller standard deviations mean that we are confident about the fact that the values of the variable are very close to the mean value. More precisely, we expect the variable to be in the range from mu2 sigma to mu plus 2 sigma. We do not usually choose the values for mean and standard deviation, but instead we would like to infer their values. Therefore, we need to collect data that we assume to be generated from the statistical model. The key mathematical object we use to perform inference is called likelihood, which is simply the product of the density functions computed for each observation. The function we end up with is a function of mean value and standard deviation, since data have been observed. The inference problem in classical, parametric statistics is solved using the maximum likelihood estimator, MLE. The idea is to find the mean and standard deviation that maximize the probability of observing the actually observed values. In mathematical terms, the problem is equivalent to find a value for mean and standard deviation such that the likelihood function achieves its maximum value. The previous problem can easily be solved in the case of a Gaussian model, as the maximum likelihood estimator is given by the mean of the observations and their standard deviation, respectively. The histogram in the plot refers to 50 observations generated by sampling from a Gaussian distribution with mean equal to 10, and standard deviation equal to 2. The estimated density in red is indeed very similar to the true one. The Gaussian model is the building block for more advanced models. For example, the multivariate Gaussian model generalizes it for multivariate data. Data are multivariate when more than one feature is observed. For example, when we measure blood pressure and heartbeat, jointly they form a multivariate sample. The main feature of the Gaussian multivariate distribution is that, when plotting the collected sample, the cloud of points has an elliptic shape. The shape of such cloud depends on the parameters of the distribution. For simplicity, let us focus on the bivariate case with two variables only, which is characterized by a vector of means, one for each variable, and a 2 times 2 symmetric matrix, usually called sigma, that describes the variability. The diagonal elements define the variability of each variable, while the others how strongly these two variables interact. Small values, in absolute value, mean small interaction. Visually, the shape of the cloud of points is circular. Large values, in absolute value, mean strong interaction. Visually, the shape of the cloud of points is elliptical. The last topic we tackle is the model-based clustering. We already saw the cluster analysis with k-means and hierarchical clustering, which are model-free non-parametric models. We now introduce a third alternative, named mixture modeling, which is instead model-based. This requires to pre-specify the number of clusters k, as in the k-means. Mixture modeling is preferred when searching for clusters with elliptic shapes, since k-means and hierarchical clustering favor clusters having a circular shape. However, being model-based, it is less flexible and struggles when the model is not suitable for the data. Without entering into details, each observation is assigned to each cluster according to a certain mix of probabilities, indicated by pi k. These probabilities are unknown and must be estimated from the data. Moreover, the cluster-specific parameters defining the location and shape of each cluster must be estimated as well. A Gaussian distribution is assumed for each cluster. In the following, we will refer to the previous model as mixture model. Inference regarding the unknown parameters is achieved through likelihood maximization, following the same idea we saw previously. However, the model is definitely more complicated than the simple Gaussian one. Indeed, the solution cannot be written in an analytical form, while a special algorithm, called EM algorithm, is used to solve this problem. We conclude with a practical example to compare mixture modeling and k-means. The leftmost panel shows some synthetic data which have been generated to represent 3 different clusters having elliptic shapes. The middle panel shows the final partition obtained using mixture modeling, setting k equals 3 clusters. Cluster analysis is almost perfect as clusters are almost perfectly identified. In particular, the elliptic shape of the clusters is recovered. On the other hand, the rightmost panel shows the estimated partition obtained with the k-means, using k equals 3 clusters. Note that, in this case, the cluster analysis is much worse. Not only the number of misclassified points is higher, but the identified clusters have circular shapes rather than an elliptical one.